In this video, we'll explore the domain of a rational function, and then we'll use Excel to identify the behavior of the function at any undefined domain values. So we've been given this function, f of x, where the numerator is a second-degree polynomial that's factored. The denominator is this linear function, x minus 3. To identify the domain, remember the domain of a rational function is all real numbers where the denominator is not 0. We see that this function would have a denominator equal to 0 when x is equal to 3. So this function, f of x, would be undefined when x equals 3 because we would be dividing by 0 if we plugged in x equals 3. Therefore, the domain of f of x is all real numbers except x equals 3. Part B asks us to use Excel to explore the behavior of the function at x equals 3. We're going to identify if the function has a hole at x equals 3 or if it's a vertical asymptote at x equals 3. I've created an input-output table where you see that at x equals 3, the function in Excel outputs this pound division by 0 error. Whenever you get that with these rational functions, make sure you put your cursor in that cell and press delete so that it's an empty cell, so that when we create the graph, it won't throw any weird errors in your graph. So I've created input values spanning from x is negative 2 up to x is 6. But you'll notice that I've input x values near x equals 3 that are sneaking up on x equals 3 from both sides. I've plugged in 2.5, 2.9, 2.99, 2.999, because those are approaching x equals 3 from the left. I did the same on the right side. We have 3.5, 3.1, 3.01, 3.001. Those are x values approaching 3 from the right side. Let's take a look at what happens with the y values. As we approach x equals 3 from the left, you'll notice we have a y value equal to 45, and 49.5, and 49.95. What value does it seem like those are approaching? If you're not sure, you can always insert another row in your table that gets even closer. So for example, I could add 2.9999 to my table, and we see the y value is 49.995. You could keep inserting x values if you really are unclear about what's happening until you get a sense of the y value. But it turns out these y values are approaching y equals 50. We see the same behavior as we approach x equals 3 from the right side. The y value is 55, then 50.5, then 50.05. If you insert another value that's even closer, like x equals 3.0001, we see the y value is 50.005. So those y values are also approaching 50. Now remember, this function will never actually be able to input x equals 3 because the function is undefined at x equals 3. But it seems like this graph is approaching the point 3, 50. As you approach from the left side and as you approach from the right side, the graph is approaching the point 3, 50. But we know that it can't actually hit the point 3, 50 because the function's undefined at x equals 3. This is telling us that there is a hole in this graph at the point 3, 50. Now, we've figured that out by using an input-output table in Excel and numerically approaching x equals 3 from both sides. We can also explore and find this answer using a symbolic approach. We have the equation given to us, but you might have noticed right off the bat that there's a factor of x minus 3 in the numerator and also a factor of x minus 3 in the denominator. So we could actually cancel that x minus 3 factor and write the function as 50 times x minus 2, and there's nothing in the denominator except 1. So really, this is just the function 50 times x minus 2. But we need to qualify that. The function, if you simplify it, still has to equal the same function. The function still has to have the same domain. You can't simplify a function, and when you simplify it, the domain changes. That doesn't make any sense. It has to be exactly the same function. So In the beginning, we said that this function f of x has a domain where x cannot equal 3. I'm just going to write that right underneath this. And I'm going to note that it's still the case that when we simplified the function by canceling the factor of x minus 3, that x still cannot equal 3. And lastly then, when we simplified it and wrote this function as 50 times x minus 2, even though you cannot see it anymore, it's still the case that x cannot equal 3. So it turns out that this function f of x looks just like a linear function, 50x minus 100, but we have to qualify that by saying x cannot equal 3. If you think about the graph of that, it would be the graph of the line 50x minus 100 with a hole at the point 3, 50. If we go ahead and graph this function using Excel, I do insert, smooth line graph, and you see it's a straight line, but in fact, there is no point there at the point 3, 50. There's points everywhere else in the real number line except at x.